All right, so the recording has started. Good, so you should see some notification coming up on that. Okay, we're up to 66 people. As I said, I expect the class to be somewhat larger than this, but there are some people who were late in, who had some registration issues and may join us late, which is part and parcel of the reason why I'm actually starting the full teaching from next week, which might please some of you all. But the work will officially commence next week. All right. So welcome again, and thank you for joining me this afternoon. And again, this class today, this time we have reserved, but the real class time is really 8 to 9 on a Monday morning. But I didn't want you to have the very first class of the semester at 8 to 9 this morning, so I put it down to 4. We will still have this in reserve, but the class time is really 8 to 9 on Monday. And some of you all I will be having for ECNG2011, so I had to juggle around the sort of spacing of the classes as well. All right, so let's get into this a bit. A lot of people, well, okay, just the sort of protocols. I will stop and ask questions from time to time. Today is not any theory, but there are things that I'll probably want some feedback on. If you need to ask something for clarification, use the hands up. I think I'll see an indication coming up at that point in time. The chat is difficult for me to read while I'm watching the screen in front of me, so I may not always catch it. But let's see how it goes. And if all else fails, then clear your throat and yell for help, and I'll try to facilitate. All right. So, as the course, or the name, sorry, says, it's signals and systems. So there are two parts of it that comprise ECNG 2011, a signal component and a systems component. So the first thing, at least to get some clarification on, is what are signals? And perhaps the best way, considering how we are communicating at this point in time, might be to consider you calling someone, or maybe even how you joined in the session. What actually happened? Now, a whole lot of things actually go on to facilitate a connection like what is there. Or if I were to pick up a cell phone and to call someone, there are a number of things that happen. And if you look at it, at least the short, what shall I say, the short version would be that, okay, of course, after all the thing about dialing the number and how the other phone hears it and so on, your particular device picks up your voice. The voice is amplified and it's clarified and processed to make it sound a little bit clearer, and then it's coded and it's sent down the road. If it wasn't coded, then it would just simply take up too much space, and the person at the other end, they will just run out of space and not be able to hear you. So there's something that goes on there. It's compressed or coded, and then it's transmitted via a transmitter at very, very high frequency, and you've seen the cell towers around the place. Then at the other end, of course, if it was coded in some form, then you have to decode it at the other side. And then your friend's phone receives the decoded signal, which is your voice, and then it comes through the speaker on the phone, or if you have earbuds or some kind of thing, so it comes through into your ear and you actually hear what happens. That is sort of the short thing. There are maybe 100 other things that happen, but in a broad context, that is what would happen. A call from one person to another. So in terms of what happens on the input side, we consider your voice to be an input to the phone, and we call that a signal. All right. And at the other side, what your friend is hearing is your voice, and that's an output. So these things that go in and come out, most cases electrically, are what we call signals. So it's something that is going in, and we classify whatever that thing is and comes out. That's the signal part. And then all of the processing that is occurring for us between what went in and what came out, we collectively put that into one box that we call the system. So in a diagram, in sort of diagrammatic form, what we have is inputs, which are the signals coming in, the system, which is doing all of the processing of that signal that came in, whatever that happened to be, and the output, which is presumably another signal that we want. So here's when you all graduate and you start to make money, right? Here's a nice car. It costs about $3 million US at this point in time. What sort of signals and systems exist here? You know, you look at that, and of course, I mean, it's doing something. So there are signals, there are systems inside of here to make this drive, all right? Or maybe a more affordable option, and I'm putting it here because this is a 100% electric vehicle. This is a Tesla. The price is only 100,000 US. What sort of signals and systems exist here? And I have a little box down at the bottom. What sort of electronics here? And we'll keep that in mind for when we talk in those of you who will be meeting me for ECNG 2012 tomorrow. So here it is in our car. And just again, let's go back, at least for the fossil fuel version. A car is a mixture of a whole bunch of things. You have an electrical part, which, at least for the fossil fueled version, you have an ignition system, you have an engine control unit, a starter, an alternator, and so on. You have a mechanical part, which is a suspension, which is what keeps you riding smoothly. You have a chemical part, a chemical system, which is the fuel and the combustion systems. It's taking fuel, either natural gas, gasoline, or diesel, as the case may be. And it has a way of converting that to vapors and igniting it. There's a biological system inside of there, which is the human, the driver. And then there's some other combinations in there. There's an electromechanical system. Most of the cars these days have something called an anti-lock brakes, or the automatic braking system, which is so that if one of the wheels, for instance, starts to skate or lose friction with the road, that the system adjusts in such a way that the remaining wheels try to compensate until we get back traction on that. That's electrical because it's electronic, because it's sensing the wheel moving, and mechanical because it's actually doing a mechanical job of applying the brakes and releasing it and so on. All of these systems have their own inputs and outputs, right? So let me ask a question. Here's the first sort of question around, and feel free to chime in with audio. Where would you think, what category would you think the airbags fall into? Yes, Justice.
Would it be mechanical?
Maybe. How does an airbag work?
When you crash into something, I guess the forces trigger the airbag to release.
Good. Okay, so at least the force part, that may be mechanical. But what about the airbag itself? What causes the airbag to inflate?
Some sort of signal.
Yeah, but what is actually causing the airbag to blow up?
Air filling in, air going into it.
Something going into it, correct, but it's not air. Anybody knows? Joshua?
Is it a chemical reaction then? Causing the inflation?
It is a chemical reaction, right? So we have part of it, so mechanical, so it's detecting something, and there's a reaction. It's a chemical reaction, correct? It's actually a very, very explosive reaction. I think the chemical is something called sodium nitride. And sodium nitride, when it ignites, explodes. It's literally an explosion, and the explosive gases inflate the airbag, which is why it blows up so quickly. So yes, it is a mechanical, it is a chemical, but then some of the ignition part of it is electronic. All right. So that maybe it's a thing that is a combination of electrical, mechanical, and chemical. All right. And that is just to give you an idea of in terms of signals and systems, how complicated certain things that we take for granted might be. The automotive, the car, and there are more signals to it than that. But just to give you an idea that when we're talking about signals and systems, right, you have to bear in mind that there's a very broad spectrum of situations that will be covered under the whole signals and systems description, right? And in fact, okay, and here I have one, the suspension system for the car, right? The suspension system, most people think that the suspension for a car just simply has to do with the shock absorbers and the springs. But in fact, the tires are part of it, the car body is part of it, the wheels are part of it, and of course the usual thing that the shock absorbers and the springs that you remember somewhere in ECNG2011 you may have done some second order differential equations with like a mass and a damper type description, or you may have done it in physics in a slightly different form. That is just part of it, and you have to add things like the tires to it, the car body to it, and the wheels, and that makes up the suspension system. The inputs, of course, and the signals are what you're seeing down at the bottom, the position of the vehicle, right? And I'm talking about the sort of vertical position of the road, how fast the vehicle is going, and whether it's accelerating in a particular direction or not. All of that caters for how the suspension system works. And the expensive suspension systems adapt depending on the road conditions. And there's an aside, I mean, I'd love to see them adapt to some of the roads that we have here available. But some of the systems on the more expensive vehicles and so on are supposed to learn about the type of road that you're driving on and know, okay, well, this road is fairly smooth, so it will relax certain, like it may change the behavior of the shock absorbers and so on. And in other cases, the road conditions change drastically, and what the suspension system may do is to increase the compression in the shock absorbers and lift the car a little bit higher up off the road. Right? So you have all of these things, and that is the whole signals and systems concept. There's a signal coming in, which is what the car is doing in some way. There's a system, which is the suspension system, and depending on what the signal coming into the suspension system does, the output will be a change in behavior. Okay? So in broad context, the signals and systems are that you have an input coming in, there's a system that is going to use that input to make a behavioral change coming out. Yeah? And in terms of examples of signals and systems here, there are all sorts of signals and systems that we have. I mean, we just mentioned some there, electrical, chemical, mechanical. Here what? The one that is in the middle of everything right now for us, our COVID pandemic. The COVID virus itself creates a situation, almost a signal and system situation for us. The virus comes in and it fakes an input into our own blood cells, and that input into the blood cell affects the DNA reproductive cycle of the blood cell that causes it to start duplicating the COVID virus. Right, so there's a biological signal coming in, and the virus doesn't have a mind of its own. It's a chemical. So a particular chemical signature comes in, and it fakes our blood cell into thinking that it's something else, and the blood cell nucleus reacts by duplicating that chemical signal, which turns out to be a clone of the virus, and that's how the virus spreads. All right. We have optical signals and systems. Some of the communication systems that we have right now work on light. So pulses of light coming. So the signal doesn't have to be an electrical signal. It can be pulses of light, bursts of light. And we have financial systems and so on. The stock market, for instance, is a type of system. The input and the output are values of shares, and the system itself behaves in such a way that it could go up, it can go down, or it can get very unstable depending on the signal that comes in. And in fact, as funny as it might seem, there are some computer programs that are used in the stock market and in stock market manipulation that are based on signals and systems theory that electrical engineers have been using for years. Yeah, so it's not limited to just the electrical. For our purposes, of course, we are concerned with predicting and analyzing the response of systems when certain signals are input to them. And for most, in fact, 99.9% of the applications we will consider, the signals are going to be electrical. All right, so you don't have to worry too much about what do you call it? About the biological and the other ones. Just know that, just be aware that those things exist, and that the signals and systems work that we are doing can actually apply in a number of other situations as well. Okay, so welcome back, everyone. I see we're up to 74. Some of you all already here may have been repeating from last time, and so that some of this, of course, will be new to you. Some of you all are doing it for the very first time, having come through a very strange first year in university life, but that's how it is. All right, I will put up the new course outline before the next class. Our next official teaching class is going to be next week, Monday morning, as I mentioned, from 8 to 9. All right, so once I just keep checking the site periodically, or I'll send a message to everyone, and you'll download and read the outline. The outline gives general information about how we're going to plan and conduct the course, and what we do at what point. All right. So the aim of the course basically is to present a base knowledge of signals and systems. And the learning outcomes are what I expect you to be able to answer questions on at the end of the 12 or 13 weeks that we happen to be here. And of course, this course is a precursor. It's actually a prerequisite for control systems, some communication systems, and then they use it in power. And we also use it in discrete signal processing in level 3 as well. Right? A lot of what you're learning here is going to apply in control systems initially. All right, so bear that in mind. This one here, and communications. Both of them use the material that we have in the course quite considerably. Controls talks a lot about, will use a lot of the techniques that we talk about, and communications use a lot of the frequency techniques. We'll be talking about things like the Fourier series and the Fourier transform, and the communications people expect you to know that fairly well. I'm also making a bit of an assumption here that you are fairly comfortable with the Laplace transform by now. You did a 1-credit course last semester, and you should have, but you should have some of the basics down, at least know how to find the Laplace transform of general basic signals, how to do things like partial fractions to get the inverse transform, how to use transform tables, and we will take it from there, but at least those manipulations are required. Most of the time, we deal with things in the S domain or in the frequency domain, and we'll get get to that as we go along. But I need you to at least, if you have forgotten what the Laplace transform and things, as I said, things like the partial fractions and simple manipulations, what they look like, go and dig back up your notes and just refresh your mind. You at least have this week to do that. Yeah. So in perspective, just to give you an idea of where it's used elsewhere in the program, right? Controls, of course, make use a lot of things like the stability issues we're going to talk about, board diagrams, which are really frequency response diagrams, block diagrams, which are models of the systems. In power, they talk a lot about transient analysis, step response, and harmonic analysis. In the computer systems thematic area, when you're dealing with things like data acquisition and so on, they talk about sampling. And of course, computers are a particular type of system called discrete time systems. And you will get an introduction to that here. And also whenever you do digital electronics, which you'll be meeting in, I think, ECNG 2004, that is a discrete time system as well. It's discrete time electronics, okay? In electronics, where I'll bounce up some of you all in ECNG 2012, when we speak about filters and feedback amplifiers, some of the things that we're doing here will actually be applied there as well. And then in communications, they talk a lot about modulation. They talk about frequency responses. So just like what is happening here, the ability of me to communicate with the 73 of you all at this point in time, that communication system, there's a lot of signal and system information with modulation and the frequency response and bandwidth terms that you would have heard already around the place happening. And of course, the signal processing to make the information clear. Yeah. Right. So in terms of what the things that I'm expecting you to be able to familiarize yourself with and to know at the end, right? At the end of the course, you're going to be able to describe linear systems using differential equations, which is what you have been doing before, and difference equations, which is a type of description for discrete time systems, okay? To describe, compare, and contrast the properties of three transforms, which is the Fourier, the Laplace, and one called the Z transform. And also to talk about the Fourier series as well. Now, the Fourier and Laplace transforms are quite similar to each other. And the Z transform is a little bit of a variation on that. So it's not really three entirely new things that you're going to have to learn. It's maybe about 1.5, all right? So don't get intimidated. And then we're going to have to use the transforms to calculate the response and to develop the response of linear and discrete time systems to arbitrary signals. All right, and then on top of that, describe the properties and applications of various standard signals, including the impulse, the step, and the sinusoid for systems analysis. As we will see coming along, it's when you have a system and you need to evaluate how the system works, you can't simply put in every single possible signal that is going to encounter. So what we do is that we take some standard test signals that, because of their properties, they tend to evaluate the signal, the system, sorry, as though it was being subjected to a wide variety of inputs. And it saves us our time, and because of the type of, we know what is going in, and we could look at the result that comes out, and based on that, we can make some assumptions about the system, whether it's going to work well or not. One of the things about systems is that you have systems, we need a shorthand approach to describing the system. English doesn't work. Mathematics and diagrams are the sort of shorthand session for the shorthand method for engineers. And we're going to look at block diagrams and transfer functions as some of the ways that we represent simple systems, and then use that to manipulate, okay? And then down at the end, to use Bode plots or Bode plots. It's a Dutch name, which is a frequency response diagram that you can take a transfer function and you, by some manipulation, you're able to get it into a particular form, and you can develop this Bode plot that will predict how the system responds over frequency, which is very important for certain types of devices, like for instance an audio amplifier or a hearing aid, or UHF radio, whatever it is. Yeah. And then also to use a technique called the Routh-Hurwitz criterion, which allows us to see if a system is stable or not. Stable systems are usually what we want, meaning that when you power it on and you put an input, that the system does what you want it to do. It doesn't go all over the place or just simply overheat, or if it has motors in it, spin up to the maximum RPM of the motor, or blow a fuse. That's the last thing that you want. What you want is that when you design something as an engineer, you turn on the power, it's sitting down there waiting for you. When you apply whatever input is supposed to be applied to it, that the output does what it is supposed to do. I'm sure many of you all have been in a situation where you were listening to people talking on a microphone, and then the microphone just squeal, the loudspeaker just starts squealing to the maximum volume. And we call it feedback, which it is. It's acoustic feedback. I'm sure you've been in a situation like that. That is a type of unstable behavior. Those are the kind of things that if you're designing a system, you want to avoid. Because what has happened there is that the audio, the amplifier has been forced to amplify something, whatever it is, to the maximum volume available to it before it actually shuts itself off. And of course, it's uncomfortable for the users. It could damage the amplifier, it could damage the speakers as well. Yeah, so that's the kind of behavior that you want to avoid. Or if you know it's likely to happen, that whatever you're designing as an engineer is able to at least address that. All right? So how are we evaluating this class? Well, because again, we're still in a fairly flexible, what shall I say, situation again this semester. There are certain things that will happen. Everything is going to be online again. At this point in time, the class is going to be evaluated by 2 assessments. One is an end of term exam somewhere, and the other one is an in-course exam. Right, I have closed book here, but since we're doing everything online, it's unlikely there's going to be a closed book, and things may change. So what we're hoping for is that if we get permission, if we get permission to have you all out in person somewhere towards the end of the semester at the exam time, that we will have a traditional sit-down 3-hour exam. And so you come in, you do the exam, and you go out of here. If not, then the online exam will probably be something along a similar line. It's not going to be, I'm hoping that we don't have to cater for things like a 48-hour or 24-hour exam, because that just makes things too difficult, and it's not, for a course like this, it's difficult to set an exam. Well, first off, the exam burden is always just about 3 hours. So to avoid collusion and various other things happening, if you have a 24 or 48-hour window, I'm really hoping, and we're hoping, as the principal said, that is not going to happen, and that if we have to have online exams, that is going to be something like the 3-hour exam with maybe a 1-hour window to download and upload the final answers to the platform. All right. Same thing for the in-course exam. I have more control over that. So it will be, well, it will be an open book exam because you'll have your notes and so on. Not closed book. But the duration will vary. I'm not too sure yet what I'll do, 75 to 90 minutes, somewhere about a halfway stage. So somewhere around week 6, 7, 8, around that time, we will have a midterm test, right? And then there are problem sets that will be posted from time to time. You're not marked on it, but we have tutorial sessions where we will go through the solutions, and your job is really to do those things, do the problem sets, practice the techniques, and come to the tutorials with your questions. So if something is not clear, or you weren't able to understand or to solve something, then you can ask a question at that point and get some clarification, and then everyone else who may have been in a similar situation can also hear as well. Yeah. And of course, I have the class questions. Those are always very important. It's always great to get some feedback from the class, and it's always nice I mean, we might be going through something, and it's always nice to ask why. All right, don't be afraid if something seems like it doesn't make any sense, or something looks a little bit strange or wonky, to challenge and say, well, you know, that's not making any sense, or you know, that why this, why not that. Those make the interaction interesting. Okay. So the teaching, well, I'm teaching it, and if you don't know who I am by now, I was ahead last time, so hopefully that should have stuck. The class times are Mondays and Tuesdays. Mondays 8 to 9, and Tuesdays 1 to 3 p.m. We have this time slot available as well, so maybe for tutorials. I'm not too sure when the tutorials are actually going to be. And as I said, because I'm also teaching some of you all in ECNG2012 as well, both classes happen on the same days, Mondays and Tuesdays, so I have to kind of juggle things around a little bit. All right, so the actual tutorial sessions, I'll let you know when, and we will organize the suit. I'm also preparing my consultation hours, which is generally when I'm available for seeing students, but you can always email me if something comes up. And there's a little mistake on the slide. It should be EDU at the end, not EDI. You know how that happened. Well, but you know my email too as well. So feel free to send it, not to the head, to my name. And then, of course, the notes and slides and any other handouts will be on my learning, which is how we are going to conduct the course at this point in time. All right. So at this point, yeah, how do I get out? Well, basically, attend classes, interrupt, as I said, tastefully, ask questions, and if you don't know anything, if you don't understand, hopefully don't know anything, if you don't understand anything, sorry, or you're unsure about something, don't wait until 2 weeks down the road to try and figure out what's happening. Try to sort it out early, and try to sort it out early and get clarification if you before it gets too late, and we could clarify, because other people may be in the same sort of position. If we have some time, usually the classes, although I have a 1 hour and 2 hour sessions and so on, I wouldn't be talking for the full 2 hours and so on. We will typically the class sessions will be 50 minutes and so on. In some cases, we may even have pre-recorded classes or lectures, and we come to class just to discuss and so on. All right. Do the problem sets, and if there are any in-class questions, try to attend them as well. The lectures are being recorded, so you can replay them and seek any clarification. I have set the properties so that you can download, but you'll have to let me know if anybody has any issue downloading the lectures and so on. Practice, plan, timetable the semester. And I know it's hard in some cases trying to find the time at home with various other distractions again, which seem to be around. But carve out the study time, and once that is there, use the time wisely, right? And most obvious, of course, get more than 50. Okay. In terms of a textbook, there is a textbook for the course, but signals and systems, the course material that I will put up here is generally enough to cover you, but it is something that is the information is widely available. All right. The library has a number of online books. I'll try to see exactly what they, just a short list, some for you all if required, but there are online texts that they could get clarification on. There are a number of videos and so on that people have for any number of things that require explanation as well. All right, so one of the good things I guess at this point in time is that material is very widely available. Okay, so we have resources, and I'm here to answer and clarify everything. All right. Yeah, somebody put in the chat that there was sodium azide. Yeah, my mistake. Not nitride, azide. Correct. A very nasty substance, but there's a useful purpose for it in airbags, as it turns out. And that's why this is on the side. That is why airbags, people can get burnt from an airbag. If you get the one in the steering wheel and there's a frontal impact, and your face actually rests on the airbag after the impact for too long, you can actually get a burn as well. So there you go. All right, so let me hear some questions about the course and expectations. So I'm opening the floor now, and let me try and answer some of your questions, at least for this afternoon. So please. Right, so questions. Okay, let me see if I can get a chat. If not, put your hand up. I've seen something. Can we start off with the convolution videos? What do you mean? If you can start looking at the convolution videos, is that it? We'll get a yeah. Okay, we'll get a convolution in a while, but there's nothing to stop you from looking at the material ahead of time. So if you want, it's there, but and if you have done it before or you want to review it, there's nothing wrong with that at all. Okay. But there's a step I want to take you all through before we get a convolution. There's some basic things that we'll have to do first. Is this course mostly mathematics based and equations to solve? Answer: yes, it is mathematics based, not necessarily equations to solve, but situations to apply the mathematics to. Right? If you look at some of the past papers, you'll see the type of questions that are typically asked. And yes, it is a math-based course. Yes, you have to do the math. And usually when we're correcting, I'm not going to penalize so much for like little mathematical errors that you might make that you're going through, and then all of a sudden a plus sign becomes a minus, and or you had something square, and then the next line you forgot to put a square in, and so on. What hopefully will happen is that as you go through, what you need to do, and this is not only for this course, but this is in general, that when you are trying to solve a problem, you should have an answer in your mind as to where the answer is likely to be. All right, so if I get some sort of answer, is that answer reasonable? All right, so you're working with equations and you're trying to solve something, and then all of a sudden you're doing okay, for argument's sake, you're doing what do you call it, an inverse Laplace transform, and then you're splitting it up into partial fractions, but somehow the division isn't working out. Chances are there's something wrong. You made a mistake there's a little error in your transcription and so on, because the problems that we'll submit to you are things that are going to require you to be able to solve in a reasonable time. Joel asked, is the course heavy on Laplace? Not to the extent that I am going to ask you to find the Laplace transform of a number of things, but we will be working in the S domain so that the manipulation in the S domain and coming back out in the time, you're going to have to know that. Right? Is the marking based on thinking and process rather than if the process was correctly done? It's actually a bit of both, because if you have a totally wrong process, meaning that you didn't understand a particular way of doing something, then you're going to be off from day one, right? Which is why it's important to sort of say what you're doing. And but a credible attempt in most problems you will get marks for. All right. Does a math course help with with the math you use in a course is purely based on, it's about 90% based on the Laplace course, which is why we developed the Laplace course to sort of give you background for this, for ECNG 2011 and for ECNG 2009 next semester, right? The math course has some other things in it, I mean, complex numbers and one or two other things. And also in parallel with this is ECNG 2013, right, which Dr. Radix does or will be doing. And that course addresses some things with Fourier series as well. So there are some things happening in parallel, all right? So at the end of the day, you have, at the end of the time, you have basically sort of 3 pure mathematics courses, which is the ENGR 1180, the ECNG 1016 and 2013, and then a sort of applied math / electrical engineering course, which is this one here, ECNG 2011, all right? So other questions? Feel free to talk to if you want to say something and feel like typing. Nothing? All right, okay. So let me see, what advice? It's right here, do the class, do the course, sorry, do the work, attend class, and don't get, what shall I say, intimidated by history. Okay, a lot of people hear that maybe signals and systems is hard to pass, or that what do you call it? That there's a high failure rate for signals and systems, or that the exams are hard. Those kind of things. Forget that. Focus on what is in front of you. There's material to be done, like all of the other courses that you have. Plan out how you're doing it and just do the work. All right. It's no harder than any other course, and if you do the work and seek clarification, that's the important thing. If something doesn't make sense, or you really are not following something at all, let me know. All right, and we'll go over it. We'll have time, and we'll spend some time to go over it. Okay, we are trying here. Well, this is week 1. The lectures will start in week 2, and I'm hoping to complete the lecture by sometime around week 10 or 11, most likely week 11. Okay, so that we're going to have a week for revision to clarify anything. The lectures and so on are online. So again, one of the things about the My Learning platform as well is that I can see when people are coming on and when last you access notes and slides and the like. All right, so it's a little bit harder to hide in the online environment than it might have been in class. All right, in an in-person class. So any other questions before we call it an afternoon? Yes, Joseph.
Do you have office hours?
Right. So I said I'm working that office virtual office hours here. I'm working on that to see what day. I have to plan on the week, and during the course of this week, I'll let you all know. All right. But if at any time you need to talk to me about something, you can email me and I can make some sort of arrangement. All right. Anything else? All right. Okay. So if not, thank you very much for attending today, and welcome back to university life in this strange world that we're in. I look forward to seeing you all, at least virtually, all the time, and definitely from next week, Monday. And we'll go forward. I want to see an incredibly high pass rate for this course. If I could get 100%, I'll be really appreciative of that. But it's in your hands. All right. So good afternoon, everyone. I will stop the recording now, and in a little while, it should be available for anyone who needs to review anything. All right. So the